In the last section, we covered the product rule and the quotient rule. Those are rules that don't give you immediately what a derivative is. They help you take complicated functions and break them up into more simple pieces. Today we're going to cover the chain rule. It's similar in nature, that tells you, it doesn't give you the answer immediately to what a derivative is, but it breaks up a complicated looking derivative into simple pieces that you should know how to differentiate. So the chain rule applies to compositions of functions. So I want to spend a couple of minutes talking about compositions of functions. So suppose we have some function m of x that's x cubed, and I guess if I want to match exactly what's in the book, minus 4x plus 7 to the 100th power. Suppose I have this function. This is you do this polynomial function to x first. It's in the parentheses. So you cube x, you subtract 4x, you add 7. And then you take the result of that and you raise it to the 100th power. This is a composition of functions, so that if you let f of u be raising to the 100th power, so f of u is u to the 100th, and g of x is the function that is x cubed minus 4x plus 7, then this function m of x is, first you do g of x, and you get the x cubed minus 4x plus 7, and then you do f to that. You raise this to the 100th, so it's f of g of x. So this is the composition of functions. It says that m is the composition of f and g. So this is m is the composition of f with g. The notation for it without the x's in it, we write m is f and then a little circle, f composed with g. Okay, so that's composition of functions, and what we'd like to know is, suppose we know the derivative of this, which we do because we know the power rule. The derivative of u to the 100th, you bring the exponent down, you subtract 1 from the exponent. The derivative of this, 100u to the 99th. Do we know the derivative of this? Yes, it's a polynomial. Again, you use linearity, you use the power rule, you split up the sums and differences, you pull out the constants. We know the derivative of this, we know the derivative of this. The question is, does that tell us the derivative of the composition? The answer is yes, and the way it gives you the derivative of the composition is by the chain rule. But before I state the chain rule, I need to say a couple of words about other ways that compositions are written, particularly in physics and engineering classes and in lots of applications. So another way to write exactly the same function, or the same collection of functions even, is to say something like, suppose y is u to the 100th, and u is x cubed minus 4x plus 7. This is a typical way of specifying functions that you just give equations, you name the independent variable, you name the output from the function, and you let the variable names keep track of part of what you're doing. So that, is there a function u of x here? Well, we didn't specify a u of x, but frequently you would say, oh, u is u of x. It's a function of x, and it's x cubed minus 4x plus 7. That's fine, there's no confusion. What about a function y? That is less clear because y is u to the 100th, so we could mean y is y of u equals u to the 100th. And then here we would have y as a function of u. On the other hand, We called this u and that u for a reason. We meant that this u can be kind of plugged in, substituted for that u. So we could also mean y equals, well, when you put this u in there, you get x cubed minus 4x plus 7 to the 100th. So if we were talking about y instead of as a function of u, if we were talking about y as a function of x, this would be the function y. Y would be x cubed minus 4x plus 7 raised to the 100th power. When you talk about the function y, if this is how things are specified for you, and you talk about the function y, which one of these do you mean? Y as a function of u or y as a function of x? And the answer is, it depends on what you say. If you say y as a function of u, you mean this function. If you say y as a function of x, you mean this function. If you take the derivative of y with respect to x, you mean this function y. If you take the derivative of y with respect to u, you mean, I was thinking y as a function of u, and you mean the derivative of this function. The reason I'm going on about this is because it encodes the derivatives of compositions very nicely. So over here in this notation, so over here in this notation, f prime of u is 100 u to the 99th. That would be the same as dy du. If we're letting y be u to the 100th and u x cubed minus 4x plus 7, then yes, f prime of u is dy du. G prime of x would be the same as, well, there's no question here. This would be the same as du dx. All right. All right. If you were paying attention, and I hope you were, you saw me have g of x that was x cubed minus 4x plus 7, and then I wrote g prime of x equals du dx equals the exact same thing, x cubed minus 4x plus 7. That would be wrong. Hopefully you noticed that was wrong. I never actually differentiated. I just wrote the same thing again. It's just a mistake. Unfortunately, I go on for about another 9 minutes, leaving that mistake on the board. Actually, when I need this in the midst of the chain rule, this derivative, I recalculate it, or I calculate it the first time correctly. But this is just a mistake that you're going to see on the board for the next 9 minutes. What it should have said was the derivative of x cubed is 3x squared. The derivative of minus 4x is just minus 4. The derivative of constant 0. So g prime of x should be 3x squared minus 4. Sorry about that. But if we ask for dy dx, well, that's the derivative of the composition, and that's what we're trying, right? It's the derivative of y as a function of x. So it's the derivative of this expression with respect to x, and it's what we're trying to have a formula for. So our question is, what is this? Whether you write it in Leibniz's notation with the d's or whether you write it in this notation with the primes, we want a formula for this. And so that's what the chain rule tells you. The chain rule. There are a number of technical hypotheses. Maybe instead of writing them, I'll just say them, but it is the derivative, or the formula, so this is the chain rule. That the derivative of f composed with g. So we would also just write f of g of x prime. You take And this is how I suggest you remember it. Don't memorize it like the product rules and the quotient rules. It's kind of a mistake to memorize these things with specific letter names in them, with specific function names. So just think of f as the outside function and g as the inside function. G is the function that's first done to x, and f is the function that's last done to x. But I'll usually say the outside function and the inside function. The chain rule says the derivative of the composition of functions is you take the derivative of the outside function, you leave the inside stuff exactly how it was as g of x, but then you have to multiply times the derivative of the inside function. Okay. For this to be correct, first we need to be able to compose f and g, so that composition has to make sense. G needs to be differentiable at x, and f needs to be differentiable at g of x. Assuming those things are true, this is the chain rule. In the notation with the d's, it's particularly simple looking. This derivative of the composition with respect to x, as we just talked about, is dy dx. This is f prime of u, which is dy du, and g prime of x is dy du. G prime of x is du dx. In the notation with the d's, in Leibniz's notation, the chain rule looks like cancellation of fractions. It looks like the du's cancel and you end up with dy dx. That is not what's happening. It is true that essentially that's the proof kind of contains that cancellation. But I remind you that dy dx is not a fraction. It's a limit of fractions. There is no separate dy, separate dx that you're dividing here. So this isn't cancellation of fractions. But the fact that it looks like it makes this formula very easy to remember. Let me do this example that we started with, and then I'll give you an idea of why the chain rule is true. It's not the complete proof because there's a serious technical detail that is difficult to get around. So let me So let's look at exactly this example. So we've got, maybe I'll write this part up here. F of u is u to the 100th. G of x is x cubed minus 4x plus 7. And we want the derivative of the composition. So we want the derivative of f of g of x. All right. What does the chain rule tell us that that is? You take the derivative of the outside function. So that's the derivative of u to the 100th. That's 100u to the 99th. And you leave the inside stuff the way it was. So you take the derivative of the outside function, leaving the inside stuff the way it was. But then you multiply times the derivative of the inside stuff. But the derivative of raising to the 100th is 100, well, the derivative of f prime of u is 100u to the 99th. But then you put in that u is what it was, the g of x, that you leave that inside thing how it was. So you get the 100, you leave the inside stuff how it was, the 99th, and then you have this inside stuff exactly how it appeared. But you have to multiply times what? The derivative of the inside stuff. X cubed minus 4x plus 7 prime. We still have to calculate that derivative. Right? It's, you want the derivative of this function. The outside function is raising to the 100th. You take the derivative of that, the derivative of raising to the 100th. So use the power rule. You bring the 100 down, you subtract 1 from the exponent, you leave the inside expression exactly how it was, but then you have to multiply times the derivative of the inside expression. So we still have to calculate that derivative. And so we end up with 100 x cubed minus 4x plus 7 to the 99th power. And then here, the derivative of x cubed, 3x squared, the derivative of minus 4x, minus 4, the derivative of 7, 0. This is the derivative that we were looking for, the derivative of the composition of functions in the notation with the d's. So in Leibniz's notation, it's just you have y equals u to the 100th, u equals x cubed minus 4x plus 7. We're after dy dx, the derivative of y, thinking of y as a function of x. The chain rule is that this is dy du times du dx. dy du, the derivative of y with respect to u. Well, here's y in terms of u, its derivative, 100 u to the 99th. Just use the power rule. Times du dx, the derivative of this with respect to x. So again, 3x squared minus 4 plus 0. Is this answer the same as the answer we got in the other notation? Yes, but if you want it to look the same, you have to put in what u is as a function of x. This is 100 x cubed minus 4x plus 7 to the 99th power times 3x squared minus 4. So yeah, you get the same thing either way. You know, it's math. It should work out the same, no matter how you do it. All right, this is the chain rule. It's what you always use to calculate derivatives of compositions of functions, assuming you know the derivatives of both the outside function and the inside function. It's extremely important, especially in physical. Well, it's extremely important not just because it helps us calculate derivatives quickly, but because of kind of its theoretical importance in lots of physics problems. So let me return to an example we've looked at before of a spherical balloon being inflated. So here's an example. Suppose a spherical balloon is being inflated at a rate of, let's say, 64 cubic inches per second. So at a constant rate of 64 cubic inches per second. So you're inflating this balloon. I'm thinking of by hand or by mouth, that you're just blowing up the balloon yourself, not that it's hooked up to a pump. 64 cubic inches per second is reasonable. My question is, how fast is the radius of the balloon increasing? When the radius is 3 inches. So that's my question. I don't give you a formula for the radius as a function of time. I simply tell you you're inflating a balloon at a certain rate, a certain volume per second. And certainly that should tell you, since you know the shape of the balloon, it should tell you how the radius of the balloon is changing. And this specifies a point in time in an interesting way. You don't say at time 10 seconds. You just say when the radius of the balloon is this. How fast is the radius changing? So can we answer this? Yes, and the chain rule tells us how to do it. So the volume of a sphere, 4/3 pi r cubed. Here will be the volume, V will be in cubic inches. And R will be in inches. And what's true is that as we're inflating the balloon, the radius changes with time and the volume changes with time. So V and R are both functions of time. We don't know what they are explicitly as functions of time, but we know that they're both functions of time. And so we can take derivatives with respect to time. So let me let t be measured in seconds. Then if you differentiate both sides of this with respect to time, on the left you get dv dt. On the right, well, this is a function of r, but r is a function of t. So this is a composition of functions. We don't know r explicitly as a function of t, but we know it is one. So what do? Well, you can use the chain rule in Leibniz's notation. This is dv dr times dr dt. It looks like the dr's cancel and you get dv dt. I'll say again, that's not what's happening, but it's very suggestive and helps one remember the chain rule. What's dv dr? Well, 4/3 pi is a constant, and then to differentiate r cubed, you just use the power rule. So we get 4/3 pi times 3r squared times dr dt. What's dr dt? It's what we're trying to find. We don't know what it is. So what we get is that at all times t, assuming the derivatives are defined, so v is a differentiable function of t, and r is a differentiable function of t, the 3's cancel here. You get 4 pi r squared times dr dt. So what happens when r is 3 inches? Dropping the units for a minute, what do we get? Well, we were told that dv dt, that we were inflating the balloon at a rate of 64 cubic inches per second. So dv dt is always 64 cubic inches per second. And now I'm going to evaluate this entire expression when r is 3, because the question was, what's dr dt when the radius, so what's the rate of change of the radius when the radius is 3 inches? So I want everything evaluated when r is 3 inches. Well, that means here I would get 27, what happened to that should have been a squared. It should have been a squared. We get 9, we get 36 pi. Right? We get 9 times 4, 36 pi times whatever dr dt is when r equals 3 inches. So the answer to this, divide by 36 pi, and we get that dr dt when r is 3 inches is 64 over 36 pi inches per second. We could simplify this, and certainly you can divide the numerator and denominator by 4 and get 16 over 9 pi. But this is the answer. This is the rate of change of the radius with respect to time. So, and we got that via the chain rule. Okay, I said that I would give you an idea of why the chain rule is true after doing examples. So let me do that now. It's actually, the idea is simple, and it does look like cancellation of fractions. And then there is a serious technical issue in the proof that I'm not going to go over, but you can read it in the book. It's idea of the chain rule. Okay, what's the idea of the proof? We want to calculate the derivative of f of g of x. By definition, that is the limit as h approaches 0 of f of g of x plus h minus f of g of x, all divided by h. This is the definition of the derivative. And then what do? Well, we use mathematician's stupid trick number 2. I remind you, stupid trick number 1 is adding 0 in a clever way. Stupid trick number 2 is multiplying by 1 in a clever way. And what's our clever way of multiplying by 1? We write this like this. Right? And so this is the same as what we had, because the g of x plus h minus g of x here cancels with the g of x plus h minus g of x there. So, I mean, that's the multiplication by 1. We multiply the numerator and denominator by the same thing, so they cancel. Why is this useful? Well, as h approaches 0, this part is certainly g prime of x. What about this part? Well, so we want to look at this part of what I just wrote. We want to look at this divided by this as h approaches 0. This is just part of what we were looking at, but it's the part that we need to analyze. So just let u equal g of x plus h minus g of x. Right? We're looking at this as h approaches 0. What happens? What happens is, as h approaches 0, well, g of x plus h approaches g of x, because g is continuous because it's differentiable at x. So as h approaches 0, g of x plus h approaches g of x, which means u approaches 0. So it's tempting to write that this is the same as the limit as u approaches 0 of, well, this denominator is now u, and if you look at, this is f of g of x, but then how do you rewrite g of x plus h? Well, g of x plus h would be u plus g of x. So you would get, or g of x plus u. So you get g of x plus u. Oh, but this, the limit as u approaches 0 of f of g of x plus u minus f of g of x divided by u, that is the derivative of f at g of x. So this is f prime of g of x. And that would finish the chain rule for us, because what we would have just shown is this part goes to f prime of g of x, and this part is g prime of x as the limit as h approaches 0. Why isn't that quite right? It's not quite right because as h approaches 0, it's easily conceivable that u keeps hitting 0. That no matter how close h gets to 0, g of x g of x plus h minus g of x hit 0 somewhere, which would make this denominator undefined, this denominator undefined, and you can't really do this. Remember, when we take the limit as u approaches 0, we're not allowing u to be 0, and yet it's possible that this denominator is. So there's a technical problem that we need to avoid. It's in the proof is in the book. I'm not going to do it. But this is the idea, and it's not surprising that the chain rule looks like cancellation of fractions in Leibniz's notation, because that's how the proof goes. This part cancels with that part. All right. So that's the idea of why the chain rule is true. I like to at least give you ideas of proofs from time to time so that you know this is a math class, not a magic class. We don't just make this stuff up. We actually prove that things work the way they work. We would like to have derivatives of inverse functions. So I need to talk about what inverse functions are briefly, and then talk about how the chain rule almost gives you what the derivative of an inverse function is. But again, there's a technical problem, and that I won't prove, or I won't do the actual technical proof to get around this problem. So first, let me talk about inverse functions quickly. You should know, ideally you should know about inverse functions already, but let me do this quickly. So suppose I've got a function, a real function. That means that its domain is some subset of the real numbers, so the numbers that you're allowed to plug into the function are real, and that b is a subset of the real numbers, so the things you're allowed to get back from the function are real numbers. So all the functions that we consider in this course are real functions. Okay. We'd like to know f is 1 to 1. Means if f of two different points in the domain of f, so two different points in A, if f of those are the same, then in fact they weren't different points. We gave them variable names allowing for them to be different, but in fact we want to say no. If the values of f are the same, then the x's had to be the same, so that two different things do not end up with the same value under f. That's 1 to 1. A lot of people describe this, you'll frequently see this described in terms of a vertical line, a horizontal line test. So if the graph of f does this, this would be the graph of a function that is not 1 to 1, because at this y value, right here, you have the corresponding points on the graph. There are 3 of them. There's one here, there's one here, and there's one here, which means there are 3 different x coordinates that all get sent to the same y coordinate by f. So that violates this. This says that if f is the same at x values, then those x values had to be the same. This is not 1 to 1. And a lot of people say it fails the horizontal line test, which is something you can use if you have the graph of the function. Right? If there's a horizontal line that hits the graph more than once, the function is not 1 to 1. All right, that's 1 to 1. There's also the notion of onto. For technical reasons in mathematics, the set B that I put here is allowed to be larger than what it needs to be. because sometimes it's kind of impossible to specify exactly all the values, exactly what the values are that f takes on. You know they're real numbers, but you may not know exactly which real numbers. So we allow this set that's called the codomain to be bigger than a set that you should have heard of called the range, which is the actual values that f takes on. F is onto this means the codomain equals the range. This is not something one typically has to worry about in the discussion of inverse functions. What I'm saying is, saying that f is onto means the set you've put here is exactly the set of values you can get from f. So the set here is the range. The range of f are all the values you can actually get from the function. If the codomain is not the range, you can always do the abstract mathematical thing of saying, I restrict myself to considering the function whose codomain is its range, and then you get a new onto function that has the same domain as the original and the same rule as the original function. It's just that this kind of abstract mathematical concept of specifying the set that you end up with has changed. Typically, we don't worry about the difference between the codomain and the range too much, because you can always restrict the codomain to being the range. But if you have a one-to-one and onto function, so if f is one-to-one and onto, so let me write f from A to B is one-to-one and onto, if and only if f has an inverse function, and if it has one, there's only one. It's an inverse function. This function, in a way it's unfortunately written, or in a way it's unfortunate that it's written, is an inverse function f inverse, and we write it as though it's raising f to the minus 1 power. It is not. This is, if you wrote other exponents here, yes, that would mean raising f to that power, but it's a special case. We write f with a superscript of minus 1 to mean the inverse function of f. Has an inverse function that goes from B to A. So it takes the values, so it takes the set that was the range or the codomain, and it gives you back things in the domain of the original function f. And what's the rule for this? Then if and only if f has an inverse function, f inverse, given by f inverse of y equals the unique x in A such that f of x equals y. So right, it undoes what f does. You give it a value for f, and it tells you the x that would have given you that y value. What this means is that if you take f of f inverse of anything, so if you compose f with its inverse, you just get y, because this is the x coordinate that goes to y, and then you do if to that. So if you call this x, then you've got f of x, which of course is y. And it's also true that f inverse of f of x equals x. This is for all y in B and this one is for all x in A. That's the inverse function. It's the function that undoes what the original function does. So the case you're probably most familiar with is something like cube root. So roots of functions are roots of x. So an example. F of x equals x cubed. Then f inverse is the cube root function, the function that undoes cubing. We have this tendency to use x both for the variable here and the variable here, even though in the midst of talking about f and its inverse, it's frequently nicer to switch variable names here and use y here. But I remind you that this variable name is just a placeholder. I could put a w here and a w here, an x here and an x here, anything here and here to give you the rule for the function. This is the same as raising y to the 1/3 power. So what do the graphs of these functions look like? Well, y equals, now if I want to graph them on the same axes and compare the graphs, then we have to do this thing you would kind of never do in a physical problem. We actually have to use x for the independent variable both places so that we can compare the graphs of the functions easily. This is y equals x cubed. It looks roughly like, it looks roughly like this. So here's y equals x cubed. The cube root. So if y is x cubed, then if you take the cube root of both sides, you get the cube root of y is x. And what does this mean? It means that if AB, let me use different letters. If AB is on the graph of y equals x cubed, then BA is on the graph of y equals the cube root of x. So for instance, 2, 8. 2, 8 is on the graph of x cubed. So that should mean 8, 2 is on the graph of the cube root. Well, of course it is. If you take the cube root of 8, you get 2. Great. So 8, 2 is on the graph of the cube root of x. So how does that mean the graphs are related? It means if a point AB is on this graph, the point BA should be on the graph of the inverse function. It means you switch the x and y coordinates. And what that means is if you take the line y equals x, this would be those points that when you switch the x and y coordinates, you get the same thing. Here's the line y equals x. And switching the x and y coordinates, well, it means you'd put this axis up, you'd spin the board. If you could grab it right here and spin it, you'd put the positive x-axis there, the y-axis there. You'd spin it around this line, y equals x. You'd grab it here and put that up there and this down here. You can do this with a piece of paper. Then you'll have to hold it up to the light to see the graph. But what it means is that the graph of the inverse function is kind of reflected about this line, y equals x. And so there's the graph of y equals the cube root of x. Okay, that's a quick discussion of inverse functions, except we really do want to take root functions. And the square root and all the even roots are supposed to be the inverse functions of raising x to the power 2, 4, 6, raising x to all the even powers. But those functions are not one-to-one, and so we have a little, well, not a little problem, kind of a substantial problem. So let's look at x to the n, where n is even, so an even integer. This function is not one-to-one. So let me call this Pn of, actually let me call it f of x for a second. F of x to the n is not one-to-one. So there is no inverse for this function, no inverse function of this, right? If, for instance, if you take x squared, why is it not one-to-one? Because positive and negative numbers go to the same place. Minus 2 squared is 4, positive 2 squared is 4. So there are two different x values that give you the same y value. This function is not one-to-one. So what do you do? Well, let's look at y equals x squared. So its graph is a parabola. Here's y equals x squared. It's not one-to-one. It fails a horizontal line test. Every horizontal line at a positive y value will hit the graph twice. Okay, so what do we do to make this function one-to-one? We restrict the domain, which technically gives us a new function, which we still call x squared, but you just have to know when you talk about the inverse that you mean technically something different. So define Pn of x to be x to the n. This is still for n even. I'm still talking about the case where n is even. Use the same rule with domain the numbers, well, x is greater than or equal to 0. And codomain, the same thing. So the set of real numbers greater than or equal to 0, I'll denote this by an r plus, so that, or no, I won't. I'll denote it by an r greater than or equal to 0. So Pn is really, it's defined to be by the rule x to the n, but you only do it to numbers greater than or equal to 0, and you get back numbers greater than or equal to 0. Why are we doing that? It means that we chop off this graph, and we only look at the x coordinates greater than or equal to 0. Oh. But if you only look at x coordinates greater than or equal to 0, then suddenly this function is one-to-one, because we've left off this part that was causing the problem. Now if you just look at this graph, it does pass a horizontal line test. And because we restricted the codomain, this function is also onto, you can get every positive or non-negative real number by raising x to an even power. So this function is one-to-one and onto, and it has an inverse, and that inverse is what we mean by the nth root when n is even. For odd n, there's no problem. Raising x to the n when n is odd is one-to-one and onto. It's a function from r to r. You can give it any real number. Take like x cubed, and you can get back any real number. So it's onto, and it's one-to-one. If two real numbers, x1 and x2, give you the same thing after you cube. So if x1 cubed equals x2 cubed, x1 had to equal x2. it's for the even powers that we have to make this kind of special definition. And all this means is you give even roots. If you're taking an even root, you should only do it to a number that's greater than or equal to 0. And then it gives you back the nth root of x, but the positive nth root. It gives you back a positive number. So you might think, oh, the square root of 4. There is no the square root of 4. There are 2 square roots of 4. 2 and minus 2. No, when we say the square root means the inverse of this function where n is 2, which means we are specifying that you take the positive one. So the square root of 2 means the positive, the square root of 4 is 2, not plus or minus 2. The square root of 4 is 2. All right. With this understanding, all the root functions are invertible, or all of the power functions are invertible if we restrict some of the domains. And so we'd like to know their derivatives. Well, we can almost get it from the chain rule, but not quite. And there are some technical assumptions that I will leave off, and the proof is again technical and slightly difficult. But suppose we have a function and its inverse. Well, then the composition of them is just the function x. But then we can differentiate both sides with respect to x. Okay? This is an equality of functions. And if 2 functions are equal for all values of x, then their derivatives have to be equal. So we can do this. The derivative of x is just 1. The derivative of this, well, it's a composition. The derivative of f composed with f inverse. You differentiate by the chain rule. You differentiate the outside function. You leave the inside stuff how it was. But then by the chain rule, you have to multiply times the derivative of the inside stuff. So times the derivative of f inverse. Right, this is the chain rule. The derivative of this side, you do by the chain rule. The derivative of x is just 1. Actually, I'd be happier right now if I had written y's here so that I could think of, let me write y and let me let y be f of x, because this will help my notation in a minute. So now I take derivatives of both sides with respect to y. I get this, I get this, I still get 1 here. And then you solve for the thing we're after, the derivative of f inverse. The derivative of f inverse at y is 1 over f prime of f inverse of y. You, of course, for this to exist, you, of course, need this to be unequal to 0. So we need f prime at f inverse of y to be unequal to 0. F inverse of y, if y is f of x, then x is, if you take f inverse of both sides, you get f inverse of y equals f inverse of f of x, but f inverse of f of x is just x. So you get f inverse of y is x. So this is just, our assumption is that f prime of x is unequal to 0. So assuming that, then you get the derivative of f inverse at y is 1 over f prime of f inverse of y, or you can write f inverse of y again as x. So this is 1 over f prime of x. In Leibniz's notation, once again, kind of like the chain rule itself, this looks kind of like something you would do with fractions without thinking. Here, when you take the derivative of f inverse with respect to y, then we're thinking of f inverse as a function of y. So we're thinking of x as a function of y. And this derivative then would be denoted by dx dy. And then this says that that equals 1 over, well, the derivative of y, thinking of it as a function of x. So we get that the stunning dx dy equals 1 over dy dx. Of course, for fractions, this is true. And because we've derived this from the chain rule, it shouldn't be a surprise that it looks like all you do is invert the fraction. That is not what's happening. I'll say it again. This is not really a fraction. It's not one quantity divided by another quantity. It's a limit of such things. But writing it in Leibniz's notation does make it stunningly easy to remember. All right. We're going, as I said, there are technical assumptions that that I'm not listing here. They're in the book. But I will be careful and only use it in cases where the technical assumptions hold. This is the main assumption. You need for the derivative of f not to be 0 at x, for otherwise you have no possibility of this formula holding. This enables us to take the derivatives of all of the root functions, and later in the book we'll be able to take derivatives of lots of other inverse functions using exactly this formula. But right now we can do the root functions. So what is the derivative of the nth root of x? So how do you calculate the derivative of this, where n is a positive integer? Well, it's not terribly difficult. This is the derivative of Pn inverse of x, where I'll say again that this is x to the n. If n is odd, that's all it is. If n is even, you have to restrict the domain to just the non-negative reals, and the codomain to the non-negative reals also. And then you can apply this formula that we just derived, but now since we're calling our independent variable, our favorite name for independent variables, x, we have to change what we've written here. We need an x there and an x there. So what the formula tells us, though, is this is 1 over Pn prime evaluated at Pn inverse of x, provided this isn't 0. Okay, but we know the derivative of the power functions by the power rule. Pn prime is n x to the n minus 1. Okay, and this is just the nth root. So what we get is that you get 1 over, and then you get, well, let me write it as you get n, and then you have this Pn, or you get n, here's the nth root of x to the n minus 1. This is Pn prime done to, so composed with, the inverse function of Pn. So there's the n minus 1, and then the P inverse of x is there. If we write this as raised to the 1 over n power, you get 1 over n x to the 1 over n to the n minus 1. When you raise something to an exponent, raise to another exponent, the exponents multiply. This is 1 over n x to the n minus 1 over n. So you get this, which doesn't look particularly like anything we've seen before until I rewrite it. So how do you rewrite this? Well, what we've just said is that the derivative of x to the 1 over n, so the nth root, the derivative of that, we just got that it's 1 over n x to the n minus 1 over n. That's what we just concluded. But this is the same as 1 over n times, x to the, dividing by this is the same as multiplying by x to the negative of this exponent. So I can just negate the numerator, negative n plus 1 over n. But then I can simplify this fraction. This is 1 over n times x to the, I have a 1 over n, and then minus n over n. That's 1. Oh, this is the power rule. But now in a case where we didn't know it already, the derivative of x raised to a power, you bring the power down, bring the exponent down as multiplication, and you end up with, and then that times x to the, you take what you had there and subtract 1. So you have 1 over n minus 1. Yes, the power rule holds for roots. But then we can compose that. Actually, there was no reason for us to only take positive integers here. We can certainly deal with x to the minus, or x to the n, where n is n is an integer. The case where n is, we're only interested in, this. We need it to be unequal to 0. So we can take the nth root, or raise to the 1 over n power for any integer n unequal to 0. This is all fine, everything works exactly the same. And so we get this for all non-zero integers n. We can compose this and use the chain rule. But let me just, if we now compose this, so if we take x to the m over n and take the derivative, how would we do that? It's the composition of two functions. You take the nth root and then you raise to the m. Okay, and then you take the derivative. Actually, there's some technical issues with if x is negative, do you take the nth root first or do you raise to the m first? If you assume that this is written in reduced terms so that m and n have no common factors, it's fine either way. What's this derivative? It's the composition. It's the derivative of the composition. We can use the chain rule and get that this is, you take the derivative of the outside function, the raising to the nth power, you leave the inside stuff exactly how it was, and you have to subtract 1 from the power. That's the power rule. The derivative of the outside function, raising to the nth power. The m comes down, you subtract 1 from the exponent, you leave the inside stuff exactly how it was. But then, by the chain rule, you have to multiply times the derivative of the inside function, which we know now obeys the power rule. So we just get 1 over n times x, and you subtract 1 from that. If you put all this together, you get something very non-surprising. You get m over n times x to the m minus 1 over n times x to the this is 1 over n minus n over n, so I'll write this as x to the 1 minus n over n. And then you have two things with the same base multiplied together. The exponents just add. I have a common denominator. So we get m over n times x to the 1's cancel. You get m minus n over n, and then if you simplify that, you get m over n times x to the, there's an m over n, but then minus n over n, which is minus 1. That's the power rule. The derivative of x to the m over n, the m over n comes down, and you subtract 1 from the m over n. So what we've just shown is that the power rule is true for rational numbers. So quotients of integers. So the derivative of x to the r, where r is rational, is r x to the r minus 1. All right. I'd like to do lots more examples with the chain rule. It's a little difficult for us to do terribly many good examples with the chain rule until we have some more interesting functions other than polynomials. So in the sections of the book that come after this, we'll talk about the exponential function, logarithmic functions, trig functions, inverse trig functions, and then we'll have lots of functions, lots of different functions, so that we can have lots of interesting compositions of functions, and we can do more exotic examples of the chain rule. But that's in future sections.